We have spent a lot of time looking at the theory of radio navigation. And now we can start looking at the navigation aids themselves, the NDB, VOR, ILS, and radar. We'll start with the most simple, the NDB, which stands for non-directional beacon. This beacon emits a vertically polarized signal in all directions, which says simply, "I'm over here." It gives no more information than that in its basic form. On aviation charts, its symbol is 3 circles of dots around a solid circle around a single dot. An aircraft with the corresponding piece of equipment, called the ADF, for Automatic Direction Finder, works on the principle of the loop antenna, and is able to detect the energy from the beacon and interpret where the beacon is. The needle on the ADF then points to the beacon. NDBs are still widely used for long-distance and local navigation. The beacons used for local navigation have a range of about 25 miles, and they are positioned on the airfield so that the pilot can locate the airfield. NDBs transmit in the medium and long wave, and so their wavelengths can be very long, which makes them suitable as long-distance navigation aids. Over the sea, they can have a range of 500 miles or more, using 10 kilowatts of power. Remember that to double the range of a signal, you have to quadruple the power. The antenna used as NDBs for long-range transmissions are in the shape of a large T, about 25 meters high and 50 meters long. You will recall that masts are ideally half the size of the wavelength, but this is unrealistic for long-wave transmissions, so some electronic loading is necessary. Short-range NDBs are fairly small towers, or simple masts. They are insulated from the ground, and this doubles the effective length of the antenna because of the reflective nature of the Earth upon the NDB ground waves. 2 types of modulation characteristics are commonly used for NDBs, N0N-A1A and N0N-A2A. The N0N part of the signal is, as we saw earlier, the continuous carrier wave, and it is ideally suited to enable the ADF equipment to establish the direction from which the signal is arriving. The A1A part of the signal periodically replaces the N0N transmission, and, being an interrupted carrier wave, is used to carry the 3-letter Morse identifier of the NDB. N0N-A1A beacons are normally used with high power outputs for long-range NDBs. The A2A designator is given to those stations that carry the NDB identifier by an A2A signal, which is a keyed single-tone amplitude modulation. N0N A2A beacons are normally used for short and medium-range beacons. Although most ADF receivers have a frequency selector range of 190 to 1750 kHz, the frequency bands which are internationally allocated to NDBs are much more restricted, from 255 to 285 kHz, and from 315 to 405 kHz. Some commercial broadcasting stations transmit in this waveband, and you may pick up their signal. This has little navigation value unless you know where the transmitter is located, but it can be entertaining. The counterpart of the beacon is the airborne equipment, the ADF, and it works on the principle of the loop antenna, which we saw earlier. But let's recap. If the NDB is directly ahead or behind the loop, then the waves will reach both sides of the antenna at the same time, and there will be no voltage difference. If the NDB is anywhere but perpendicular to the loop, the waves will arrive at different times at the 2 elements of the antenna, and will cause a current to flow. A figure of 8 polar diagram of signal strength can be plotted as the antenna is turned or the transmitter moves around the antenna. How is this figure of 8 pattern constructed? In one complete revolution of the loop antenna, each vertical element will turn through 360 degrees. If we follow the red-colored side of the loop antenna and plot it against the sinusoidal shape of a radio wave, we see that the antenna turns through the positive side of the sine wave from 0 to 180 degrees. It then turns through the negative side of the sine wave from 180 to 360 degrees. At the same time, the other, blue element of the antenna is following the opposite pattern. It is 180 degrees out of phase. If we place the two patterns together, we get a figure of 8 polar diagram of the beacon signal strength at all points of the loop antenna. There are two positions at which there is no difference between the strength of signal received by the two vertical elements of the antenna: at 90 and 270 degrees on the sine wave. The signal difference is said to be zero or null, shown at positions B and D. The null point is chosen over any other phase as a datum point, because small angular movements from zero produce a greater electrical response, and are therefore more detectable than an increase to an existing response. Suppose the transmitter is at position B. If the loop antenna is rotated slightly in either direction, signal strength will increase. By finding the null position, zero signal strength, the bearing of the transmitter from the loop can be determined. Having two null points, one in front and one behind the antenna, means that one cannot say whether the NDB is in front or behind. This is resolved by using a second antenna, a sense antenna. The sense antenna is designed so that the received signal produces a current of the same strength as the maximum current in the loop antenna. Consequently, the radius of the polar diagram of this single pole antenna is equal to the diameter of each of the loop antenna circles. It is arranged for the field from the sense antenna to be in phase with one of the elements of the loop antenna. Here, we see it is in phase with the left-hand element. The resultant polar diagram of signal strength is known as a cardioid, which means that it is heart-shaped. If, for example, the transmitter is at position D, the loop antenna senses a null, which means the transmitter is either at D or B. If the loop is rotated anti-clockwise, the combined polar diagram of signal strength will rotate with it, and signal strength will increase, confirming that the beacon is at position D. If the loop is rotated clockwise, the signal strength will decrease. If the transmitter were in position B, the reverse would be true. Thus, if anti-clockwise rotation produces a stronger signal, the bearing is correct. However, if it produces a weaker signal, the bearing is a reciprocal. The signal accuracy can be further increased to that required by ICAO, namely plus or minus 5 degrees, by reversing the polarity of the sense antenna to produce a right-hand cardioid, and then switching between the two about 120 times a second. Because it is impractical to have a movable loop antenna on modern aircraft, current versions of the ADF combine both loop and sense antenna within a teardrop-shaped housing, mounted as near as possible to the center line of the aircraft. This has a fixed loop with 4 elements, 2 aligned with the fore-aft axis of the aircraft, and the other 2 with the lateral axis, rather like 2-cross loop antennae. The electrical fields produced in the loops are transmitted to a goniometer, a device for measuring angles. This consists of 4 field coils, which reproduce the electromagnetic field detected by the loop antenna. Within these 4 elements is a search coil, which always wants to be aligned to the null position in the electromagnetic field. Here, we see the NDB at 090 degrees to the fore-aft axis of the aircraft, and the search coil is in the null position. If the search coil is not exactly in the null position, because the aircraft is changing its angle to the NDB, a voltage will be generated in the search coil, which is applied to a motor, which rotates the search coil until it is in the null position. The shaft, which at one end turns the search coil, at the other end turns the needle on the ADF display in the cockpit. Here, we see 2 modern ADF control panels made by Bendix King. The one without the dial is digital, but they both operate in the same way. The first thing to do when planning to use an ADF is to find its location, its designator, and its frequency, all of which can be found from aviation charts. Here, we see the NDB at Manston, with a designator MTN and a frequency of 347 kHz. There are several others on this extract. See if you can find them. A complete list of NDBs is held by each country's civil aviation authority. Here is an extract from the en route section of the United Kingdom Aeronautical Information Package, the AIP. More than likely, you will enter the NDB designator into your flight plan, which your autopilot will follow. But if you are selecting the NDB manually, you select the ADF button and enter the frequency. You must then check that you have selected the correct NDB by listening to the Morse identifier. Aviation charts contain the Morse alphabet. Pressing the antenna button deactivates the loop antenna, and the audibility of the A2A identifier should improve, but the bearing information must obviously be disregarded. In some NDBs, the amplitude of the carrier wave remains constant, and therefore it is impossible to achieve an audible output from the receiver. On Jeppesen maps, the 3-letter identifier of such stations is underlined. By selecting the Beat Frequency Oscillator button, BFO, an oscillator within the ADF is activated, which creates an audible output from a non-modulated N0N and A1A signal. The bearing reading must be ignored, as the loop antenna has been isolated. Let us say that the carrier wave is transmitted at 260 kHz. The BFO generates an alternating current, which differs from the incoming carrier wave frequency by 2 kHz at 262 kHz. Both signals are fed into a frequency mixing unit, a heterodyne unit. The output comprises 4 signals: the 2 original signals, the sum of the 2, which is 522 kHz, and the difference between the 2, the beat frequency, which is 2 kHz. It is this 2 kHz signal frequency that is required, because it is in the audible range, and so the Morse ident can be heard. On most modern aircraft, this BFO function is done automatically. Finally, the test button, when depressed and held, will swing the needle roughly 90 degrees to show that it works properly. Releasing the button sends the needle back to its bearing reading. Try it. This is a digital ADF controller. If you needed the beat frequency oscillator, you would press the BFO button to hear the ident of N0N A1A beacons. In this lesson, we have looked at the principles of operating an NDB, polar diagrams, and how the instrument in the cockpit is operated. In the next lesson, we look at how to interpret the ADF.